I would like to give a formal introduction to the resource person for the day. Professor Shay Singh Bhakar is the Vice Chancellor of ITM University, Gwalior, Madhya Pradesh. He has been a former director at Prestige Institute of Management for almost 2 decades. Sir has completed his PhD in Management, MBA Operations Management, and BE in Electronics and Communication, and Diploma in Electrical Engineering. Sir has many awards and achievements to their credit. To name a few: Truly Global Educator by Global Leadership Awards, Madhya Pradesh Ratan by Madhya Pradesh Press Club, Pride of International Educational Excellence Award. Sir has been guiding many PhD students, and also Sir has guided one business school to get NAC A accreditation 12B. Also, there are more than 60 research methodology workshops, 25 case writing workshops, and many executive training programs that have been organized and implemented. And there are 18 national conferences and seminars that have been where Sir has delivered as keynote speeches. Thank you so much, Sir, for accepting to be the resource person for today's session. Over to you.
Thank you. I will try and share my screen. Let me see. Is my screen visible?
Yes, sir.
Okay, I will go for slideshow. All right. Okay, we will be talking about measures today, and once we've gone through the measures, maybe if time permits, we'll look at their reliability, validity. I would also try and show how to compute reliability and validity of given measures. Validity would take longer time, so I don't know whether we'll be able to do that, but reliability I will be able to show how to compute, because that just takes about a couple of minutes. So first we'll try and understand what measures are, and then we will look at how to compute reliability, validity, or what reliability, validity of measures are, and how do we compute. I don't know whether reliability and validity is a separate session. It is possibility. If it is a separate session, then I'll skip that and I'll concentrate only on measures. So is there a separate session on reliability and validity? All right, so don't worry, we will have a look at that as well. Right, so why do we need measures? We are all conversant with the measures that actually can measure our weight, our height, or length, width, and so on. But in research, we also need to measure emotions, attitude. We also need to measure other variables that are not amenable to any direct measurement using any such scales. So we therefore need to measure them using indirect methods, that is through attitude measurement scales. But before I talk about, I'm not going to actually look at attitude measurement scales today. I will be looking at how do we actually measure using those scales. Actually, and that is that every measurement scale that you use will use one method of measurement out of the ones that I'm going to talk about today. And they are also called data types. These measurements are also called data types because they result from different scales, but then the data that comes out of these measures have different characteristics, and therefore they are also called data types, right? So we will be looking at these, and then the basic measures, and then if possible their reliability and validity. All right. What is a measure? In case of for the purpose of research on the areas that cannot be directly valued or cannot be directly evaluated. For that, we use indirect methods. We call them measures. A series of items arranged according to value for the purpose of quantification is called measure. What does that mean? What it means is that you can have, say, two values, 1 and 0, or 1 and 2. It can have multiple values, 1, 2, 3, 4, 5. It can also be, instead of a numeric value, it can also have a phrase. Like, say, in case of gender, like male, female. In case of, say, satisfaction, high satisfaction, average satisfaction, low satisfaction, or very high satisfaction, average satisfaction, low and very low satisfaction, or like that. So we can have two or more values that can be given some weightage, or that can get some weightage, which is called measure. And therefore, we call it a series of items that can have value, that can be used for the purpose of quantification. And they will be on a continuous spectrum, then only we can measure them. Let us see. These are the properties of a good measure, these four, but they all will not be there in all measures. The measure should uniquely classify the items that are being measured. And the items can be individual people, products, they can be services. Okay, the items can be any characteristics. Items can be also characteristics. So properties of good measure is that a good measure should uniquely classify the people, products, and services based on their characteristics that are being measured. Preserves order. That means the values, it preserves those order of values, lowest to highest or highest to lowest, preserves order of that. That means it can order the, say, products or people or services based on their characteristics, like people based on height. A person who has a particular height, then a taller person, then a taller to him. That means they can be arranged in rank order. Preserves order means that rank order can be assigned to the people, products, or services that are being measured. Their rank order can be decided. So that is the second property of a good measure. And third is equal intervals. Equal intervals means the measurement are on equal intervals. That means if a measure has 5 values, then value 1 to 2, the gap will be, there's a particular gap. Then between 2 and 3, or second value and third value, the gap will be same as 1 to 2. And it remains same for all the intervals. Like, say, very low to low. If there is a particular gap, low to average, there is another gap, right? But since it is perceptual, since very low and low and say average depend on individual perceptions. So there can be different gaps between, say, very low to low and low to average. But if you have a numerical scale, 1, 2, 3, 4, 5, gap between 1 to 2 would be the same as 2 to 3, and will be the same as 3 to 4 and 4 to 5. That means this is the third characteristics. That means a good scale or a scale can be considered as good if third characteristics is also there. And fourth is natural zero. That is, measurement starts from zero, either positive side or negative side, or both sides, but there is a natural zero in the measurement. Then we can, if we have these four, see, if only one characteristic or one property is satisfied, that is considered as the lowest measure. The quality of measure is the lowest. If 1 and 2 both are satisfied, that is better than the first one, but worse than the other two. And if first 3 are satisfied, then it is better than the first 2 and worse than the last one. And if last is also satisfied, that is the best measure. That means it has it uniquely classifies people, products, services, etc. It preserves order. It has equal intervals, and it has natural zero in the measurement. Then the scale is considered as the highest class scale or the best measure, right? So we will look at the 4 basic scales that are there, and we will see what properties are satisfied by each one of them. The first one is nominal scale, right? The 4 scales are nominal, ordinal, interval, and ratio. These are the 4 different measures that can be used to convert a subjective property into an objective value. Okay, scales or measures are used to convert subjective characteristics into objective values, right? So nominal scale is the category, the lowest category scale, because it only, if you look at the 4 properties, uniquely classifies. It only allows, or it only does, it only uniquely classifies the people, products, or processes or services that are being evaluated using this scale, right? So nominal scale basically is used for identification, and in that it can also be used for classification. That means if it can identify different people, it can also classify them. Like say, gender is a nominal scale, right? So it identifies male, female, right? And when it identifies male, female, it can be used for classifying the people into 2 groups, male and female. When I say people, in case of research, it will be the sample. That would be classified into the 2 groups, male and female. Similarly, a nominal scale can also take multiple forms. It is not necessary that it will have only 2 categories or 2 classes. It can have multiple categories or multiple classes, right? So like say education qualification. Education qualification, when we talk about, if we don't consider classes like 1, 1st, 2nd, 3rd, 4th, 5th, instead of that, if we use certifications like matriculation, degree, postgraduate, or doctorate, if we consider these, then it will come under nominal scale, right? And it can be used to classify people or samples based on the qualification of individual participants or individual sample elements in the sample. So a nominal scale is one that can be used to classify the sample into different categories, and it is basically used for identification, and that is the characteristic that can be used to classify the sample elements into different categories. What are the characteristics of what are the scale properties? It uniquely classifies. That's it, right? So it will, like, there are two names I have written, Sammy and Barry Bonds. These are two people, and they may have serial number 2125. They can be classified that who is Sammy Sosa and who is Barry Bonds. Any names can be taken, right? So if you look at a nominal scale, the nominal scale is used for classifying. Where do you use it for in the research work? You use it for dividing the sample into different groups, and then maybe comparing different groups. Like, say, if you are measuring, say, motivation level of say, faculty members in an institution. So you can divide faculty members, say, based on education. Ones who have who are postgraduate, ones who doctorate, post doctorate, right? So you find you can classify them in 3 categories, and then you can look at what is the motivation level of each one of them, or is there any difference in motivation to teach based on the education qualification. Age also can be a nominal scale when you use different categories of age and not actual age in number of years or days. When you use categories like, say, youngsters, young people, elder people, like that, or you classify 18 years and below, 18 to, say, 30, 31 to 45, 46 and above. When you use these categories, use these groups, then you can, this can also be considered as nominal scale, because it can be used for classifying the respondents into different age categories, right? Even income can also be used as nominal scale. Low income, middle income, medium income, higher income. So people belonging to low income would be classified in one class or one category. People having middle income in the second category, high income in the third category. So am I making sense? Are you able to understand that what nominal scale would be? Because later on, we in research will be using that. And I'm not sure whether you have somebody has covered these, but if somebody has, good, that it will be a revision. Ordinal scale. Now, in first nominal scale, what we did was that it uniquely classified people or products or services into categories. Now, ordinal scale is a one step better than the nominal scale, and it also ranks the people, products, or services based on the characteristics that we're measuring. That means it meets 2 characteristics of good measure. The second is preserves order. That means it ranks order the products, processes, services, etc., based on characteristics of characteristics that we measure. So that means, suppose if we want to measure the satisfaction level of, say, customers who are using a service, like, say, satisfaction level of respondents to this session, if we want to measure. Now, it can be measured using ordinal scale. That is very high, say, ordinal, the scale can have values like very high, high, average, low, very low. It can, so it satisfies 2 properties. it uniquely classifies. That means people who would rate this session as very good or on quality of session very high, they will be classified in one class, people who have rated it that very high. Second group would be one who have rated it as high. Third group would be the one who would rate this as average. Fourth group would be the one who would rate it as low, below average or low. And fifth group will be the one which will rate it as very low, right? So if we evaluate a characteristics like that, and we can use that for classifying, uniquely classifying people or products and services, it will be a ordinal scale. Now, next scale that we're going to use and the ordinal scale, there is always a confusion in the minds of beginners to research. But I'd try and clarify that today. When you're measuring, say, satisfaction level or quality of session that you are attending today, it can be done in two different ways. One is that you can measure it using very high, that means phrases, low, average, low, very low. You can also use numeric scale, like say 1 to 5, right? 1 indicating lowest quality, 5 indicating highest quality, right? So even that would be that you can evaluate 1 to 5. If you do that, and if you use phrases very high, average, low, very low, right? What is the difference, and whether both would come under ordinal scale, or one would come under interval scale and one will come under ordinal scale. Now, this confusion we'll try and resolve today. When place and show, this is an example that I have given. You can rate a show, you can rate a place, okay, and you can even evaluate wins, very high win or high, average, low win, etc. Now, next I said, and I'm going to compare these two. So I'm clubbing these. Interval scale, it also uniquely classifies, it preserves order, and intervals are also equal, right? Intervals are also equal. Now let's see whether you are able to differentiate between an interval scale and an ordinal scale. Now, I said that quality of session that you are attending today can be evaluated using phrases, very high, average, low, very low, or it can be evaluated using a scale of 1 to 5, where 5 indicates highest quality and 1 indicates lowest quality. In case of phrases, you can also use codes for them, wherein 1 will be the code for say very low, 2 would be the code for low, 3 would be the code for average, code 4 will be for high, and 5 will be for very high. When you put it in an Excel sheet, you would not actually write phrases, you would probably write the numbers, the codes that you have used. And if you have evaluated using interval scale, there also you would be using numbers, because you have evaluated the quality of the session in numbers, right? Now, if you do that, how do you understand that one is a ordinal scale, the other one is an interval scale, or which one is an interval scale, which one is an ordinal scale? Basically, in the first case, when you have phrases, the difference between phrases can vary. And it can also vary between people, or between people who are observing, between respondents, and it can vary for the same respondent between the phrases. Like say, between very low and low, there is a gap, there is an interval, and low and average, there is another interval. Now, these intervals may not be equal for different people. One, and they may not be equal for the same person measuring a particular characteristic. When it is not equal, it is the ordinal scale. When it is equal, it becomes an interval scale. That is the difference between these two. So when you are using phrases, the interval between different values they may not be equal. So that means it would be an interval scale. And same characteristic or same variable, when we measure using a numeric scale 1 to 5, the interval between 1 and 2 would be 1, 2 to 3 also would be 1, 3 to 4 also will be 1, 4 to 5 also would be 1, and so on. So therefore, the intervals are equal. And since the intervals are equal, it will be called interval scale. Now, since we had also written numbers, codes under the phrases, does a ordinal scale convert itself into an interval scale? If we, while collecting data, we also write codes under the phrases? No, it does not. Even if you write codes under the phrases, the scale does not convert into interval scale, because the respondent is going to read the phrase and take decision based on phrase. And some respondents may actually consider those numbers as scale values, but majority of respondents would consider them as codes, and the phrases as the actual measurements. Therefore, a scale or a measure that uses phrases to measure the values, it will be classified under ordinal scale, and is a measure that actually measures, which has equal intervals between different measures or different values, would be classified under interval scale, right? So you understand the two examples given are consumer price index and Fahrenheit temperature. Now, you would understand when we look at ratio scale, how or what is the difference between the interval scale and a ratio scale. Fahrenheit does not start from a 0. We all know that. Fahrenheit temperature scale, and therefore Fahrenheit would come under interval but will not come under ratio scale, because it doesn't start from 0, base 0. Now, ratio scale has property of, it satisfied all the characteristics of a good measure. It uniquely classifies, it preserves order, the intervals are equal, and there is a natural 0. Right. So since we have all these four in a ratio scale, these are the four properties that are required in a good scale. And that means what could be the examples of ratio scale? Then your weight, height, length of any item, you find that it starts from 0, and then you can measure these values. Income, actual measurements, all actual measurements using different measuring scales would be considered under ratio scale. Actual measurements like height can be measured in centimeters or inches or whatever. It will come under ratio scale because it starts from 0 and then whatever is the height. Weight, same way, would also be considered under ratio scale. Even income, it may get measured into minus plus, but it has a base 0 for considering minus and plus values. So it will also come under ratio scale, right? So ratio scale and interval scale, there is only a minor difference And the minor difference is that ratio scale has a base 0, and that means actual measurements can also be all. Kavita, I'll come back to you. Let me complete this. When there is a base 0, then a interval scale can be considered as a ratio scale. That means all actual measurements will come under ratio scale, majority of them, not all. And interval scale are indirect measurements, would come under interval scale, even if you use numeric scale. All right, Kavita, you can ask the question, or are you typing in? It will be difficult for me to see the chat. Can you unmute and talk?
So can I read it out?
Yeah.
So sir, it says if we take sales growth, market price of the company, will it be a ratio scale?
Sales growth, actually, sales is also a actual measure. It will be a ratio scale.
Okay, and sir,
Yes.
there's one more question. It says, is Likert scale ordinal or interval?
See, Likert scale per se is an ordinal scale. When Likert scale is an ordinal scale in any case, but nowadays a lot of people use modified in Likert scale. That means Likert scale uses phrases, but people use numerical scale instead of phrases. Then it converts into a interval scale. Actual Likert scale is a ordinal scale.
Thank you so much, sir. Thank you.
Welcome. Any more questions you can ask? Any questions if you have, then we will move on.
Participants, if you have any questions, you can put it in the chat box. I will read it on your behalf and sir will answer. So there's a question from Ms. Charu. She says, can you please quote an example where Likert scale is interval? Sir, am I audible? Dear participants, I think there was some network issue on sir's side. He'll be joining soon.
All right. So before I start, there is a chat. If we convert these phrases into 1, 2, 3, 4, 5, then it will be interval scale. No, it will not convert into an interval scale. Once you have used phrases and then you write numbers underneath that, or write numbers later on and use them for analysis, it does not convert into an interval scale. It remains an ordinal scale, right? So it doesn't, once you've collected data, scale cannot be used after that. Okay. I'm sorry, I had lost my connection. My Wi-Fi was, it went off. So I have now connected my hotspot. And are you able to hear me?
Yes, sir. You're
Yes, sir,
clearly
you're
audible.
audible, sir.
Okay,
No
that's
problem.
good. That's good. So I had an issue with my my connection. All right. So we were doing these scales. Now I said I will spend some time on why or how scale come into picture for identifying what statistical methods can be used for analyzing data. Okay, so as I had said, that there are basically three bases of selecting statistical tools. One is the objective. What do you want to achieve? What question do you want to answer using that statistical tool? So one method is one classification base of all these statistical tools, or one basis of selecting statistical tool is the objectives. The objective. The second is the number of variables. A single variable, that means univariate, bivariate, or multivariate. Whether the study is a univariate study, bivariate study, or a multivariate study. And the third is the measurement use, the scale of measurement, basic scale of measurement that has been used. So these are the three bases when they combine together to decide which statistical tool will apply. I will give you a few examples how they actually combine together to decide which method will be used. Like say, if you are evaluating, say, satisfaction with this, say, session, using phrases, okay, using phrases. And second is, if you are using a interval scale, that means you are using a ordinal scale or an interval scale. When you are using ordinal scale, and if you want to, if you want to differentiate between two groups, say based on male and female participants in this workshop, then if you are using ordinal scale, then non-parametric tool will be used for differentiating two groups. Non-parametric tool will be used, right? Man Whitney, you, Kaiser, this one sample, two sample KS test, two sample Kolmogorov-Smirnov test, etc. Right? Those will be used to differentiate between two groups. But if you use interval scale, then parametric test can be used. That is, t-test can be applied to differentiate between two groups, right? So, when you use these scales, nominal scale and ordinal scale actually provide non-metric data, okay? Nominal and ordinal scale provide you non-metric data. And therefore, only non-parametric tools, statistical tools can be applied on the data that is received through, or that has been, that has been obtained through these two scales. the interval and ratio scale result into metric data. And therefore, you can apply parametric tests, statistical tests, using the when you've collected data using interval scale or ratio scale. Understood? So if everything else is same and only the scale is changed, then also you find that you can classify into, you can use whether you can use a parametric test or a non-parametric test, right? So non-metric data, if you have non-metric data, you can only use non-parametric statistical tests. When you have metric data, you can use parametric tests. All right, and the scales result into metric and parametric. All the tests, starting from univariate, bivariate, multivariate, wherever the requirement of metric data is there, and where the tool is parametric, you need to use interval or ratio scale. And if you've collected data using nominal or ordinal scale, you can't use any parametric test. So if you've understood that, that means the scales are absolutely important. They divide, they restrict your selection of tools. That if you've used nominal and ordinal scale, you can only use non-parametric statistical tools. And if you use interval and ratio scales, you can use both, that is non-parametric or parametric, because it satisfies the requirements of a parametric test, and therefore you can use either. All right, and therefore you find that good studies wherein the parametric tests are essential use interval or ratio scales. All right. I don't need to talk. And another issue is, look at the second point here, composite measure, or I call it summated scale. Composite measure or a summated scale. You find that whatever attitude you want to measure, it is not generally measured using single item or single variable, right? You use multiple items in a single instrument or single measure, right? When you use multiple items in a single measure, and for the purposes of differentiation, for the purposes of relationship, you would use the total, right? Total of the scale. That means if there are 10 items in a scale, and say all the 10 items are measured on a scale of 1 to 5, then when you total them, for each respondent, you would find the total of 10 items, and maximum it can go up to 50, because the highest value for each item is 5. So even if the respondent has given 5 to all, it still would not go beyond 50. So highest value that you can get is 50, and the lowest value that you can get is 10 multiplied by 1, if you are using 1 to 5 scale. So 10, it will vary between 10 to 50. And this, you know that whenever you collect data and you want to use statistical methods using software like SPSS, they have a set set method of reading data. That means if you are using statistical tools on software, the data has to be fed into that software in a particular pattern or in a particular arrangement. That is, all the respondents should come in rows and all the responses should come on columns. That means responses means the questions, responses to the questions. That means questions will be in columns and respondents would be in rows. Okay. And the total that would appear as a column. Right. So when you want to differentiate between two groups, that means you'll be differentiating between, or you will be having two columns, and you will be differentiating between those two columns when you're using the software SPSS. All right. So for majority of cases that you would come across measuring different characteristics or attitudes, you would be using composite measure, or we call it a summated scale, right? And you would not use a single variable or a single item, if we call it, in a scale. Now, next, we're talking about when you're using a measure, whatever measurement you are doing, we want to be sure whether the measurement is reliable, whether the measurement is valid, and the sensitivity of the measure is perfect. Now, these are the things that are essential in a measure. Whenever you develop a measure, you need to ensure I'm not going to look into the attitude measurement scales per se, because there are standardized attitude measurement scales, but that you can find them anywhere. I'm not going to look into that, but I'm going to look into that when you have developed a scale, or when you have developed a questionnaire, or when you have developed a measure, what are the essential characteristics of a good measure? The essential characteristics of a good measure are that it should be reliable, it should be valid, and it should have right sensitivity. Now, let's look at each one of them. What does it mean that the measure is reliable? Or what does reliability mean? Reliability means that the measure is stable. That means it is going to get similar values when applied multiple times. Okay, when you develop a measure, like say in case of measuring weight, say if you are using a weight like a kg or something of that sort, every time you measure any item using the weight, it is going. It's a if you use a proper scale, like say digital scale, you would find it will always give you the same value. That means the scale is reliable. Similarly, even if you use subjective scales, the scales that are used for evaluating subjective characteristics, they should also be reliable. Okay. Now, every time that you measure the same characteristics, the scale will give you the similar values if it is measured of the same people or same products or same services. Then it should give the same values. Then it can be considered as reliable. Okay. It is also all the items in a measure, in a reliable scale, must measure single characteristics or single variable. And you should not combine different variables in a measure. That means for every variable, there is a separate measure that needs to be used. And when we say a single measure, that means the items used in a measure should relate to each other. Understand? The items used in a measure should relate to each other because they are measuring the same variable, different characteristics of the same variable. You find there will be a relationship between the items, but those relationships should not be such that the relationship between them becomes, so like say if you are using correlation, it becomes 1. Then the 2 items are not needed. Then only a single item would suffice, right? So when we look at reliability, all items in a scale should relate to each other. That means when we look at the overall reliability, when the relationship is there between the, higher the relationship between variables, higher will be the reliability of the scale. We call it internal consistency. This relationship between the different items in a scale is considered or is called internal consistency. And the reliability coefficients that measure internal consistency are split half, Cronbach's alpha, Guttman, and so on. So there are number of ways internal consistency can be measured. Similarly, reliability can be, can also be measured twice. That you can measure the same characteristics twice. We call it, reliability that is between the measures that between the two values that you get by applying a scale and collecting data twice. Rate, test retest. We call it test retest reliability, right? So we can have a test retest reliability or a internal consistency reliability, right? So reliability, and so we've talked about reliability to degree to which measures are free from random error and therefore yield consistent results. So this is one part. This is when we measure test retest reliability, then this will be applicable. But majority of time, we only measure internal consistency of the scale. That means the relationship between different items, that all the items that have been used in the scale are measuring the same variable. Then the scale is reliable. If some of those items are measuring something else and are not measuring the same variable, then the reliability will become poor. Okay. You can look at this. The reliability is the degree to which a measurement technique can be depended upon to secure consistent results upon repeated applications. That means the outcome of the measurement process is reproducible. Similar results are gotten over time and across situations, right? So that is reliability. And as I said, that each, in a multi-item scale, each item should also measure the same variable. And therefore, there should be internal consistency between the different items of the scale. Then we can consider it as reliable. Okay. Next is validity. Validity is more to do with whatever results you've got, whether they can be applied or they can be interpreted for the population. Right? Basically, why do we carry out research? Research we carry out for the population. But we don't use population for carrying out research. We use samples to carry out research. And based on the samples, whatever results we get, we need to interpret those for the population, right? So what is validity? Validity means that whatever results you get for the sample, it should be applicable to the population, right? So that means the degree to which any measurement approach or instrument succeeds in describing or quantifying what it is designed to measure. The measurement process actually measures what it purports to measure. What it means is that when we are trying to evaluate, say, in an organization, the level of motivation, okay? Say we are trying to measure whether the motivation is high, average, or low in an organization, right? So, and we take only a sample out of the organization, say the organization has 10,000 people working for it, and we select a sample of 200 and measure their motivation level. Now, the measure will be valid, or this method would be valid only if whatever motivation level we get out of these would also be similar to the motivation level of all the employees on the organization. So validity indicates that the results can be interpreted for the population, right? So that, and also that it measures what it purports to measure. That means if you say that this measure of we are developing a say measure to evaluate satisfaction level of customers with a particular product, then it should only measure satisfaction and it should not measure anything else, right? And next is sensitivity. Now, sensitivity is the number of items in the scale. If you use on a scale, you can use it can be 2-item scale, 2-value scale, 3-value scale, 5-value scale, 7-value scale, 9 or 10-value scale. Okay, then the 2-value scale would have the lowest sensitivity, like say gender, male, female. The sensitivity of this scale is the lowest. Or if we use phrases high and low, sensitivity of the scale is low. If we use 1 and 2 in numeric scale, the sensitivity of this scale is low because there are only 2 values. If we have more values, like say 3, then we can have 1, 2, 3, or we can have low, average, high, and so on. So sensitivity of this scale is better than the 2. And if we have 2 items, 2 levels, so the number of levels in a scale would indicate sensitivity. Now, what is the importance of understanding sensitivity? The sensitivity of the scale should be such that the respondents on whom you are applying this measure should be able to differentiate between the 2 values in a scale. Like say, if you are using a 1 to 5 scale, and if you are measuring, say, satisfaction level of people with a particular product, now people should be able to differentiate whether this product, their satisfaction with that product should be evaluated as 4 or 5. So if they are able to differentiate between that, then the sensitivity is okay. But if they are not able to, let's say, like if you use a 10-point scale for measuring satisfaction level, customers would not be able to differentiate between a score of 9 and score of 10. For a particular level of satisfaction, they would be confused whether they should give a score of 8, 9, or 10. That means some of those respondents would give 8, some will give 9, some will give 10 arbitrarily. That means the results would be less than accurate. So even if you use more sensitive scale, it can result into poorer responses if the respondents are not able to respond to the level of sensitivity that you're using in your scale. So sensitivity should be very carefully used. Like say for kids, if you use a 5-point scale for kids, even if you use the phrases, it will be difficult for them, say kids below 5, to differentiate between the 2 values. But if you use a 3-point scale, they will easily be able to do. And that is the reason why kids below, for any scale that is being used for kids for below 5 years, it will always be a 3-point scale or 3-value scale and not a 5-point or 7-point or 10-point scale, right? So sensitivity is also as important as reliability and validity. Though you can't evaluate sensitivity after collecting data, whereas reliability and validity can be computed once you have collected data, right? So therefore, sensitivity has to be carefully decided based on your target respondents and their educational qualification, etc. Because if you are measuring, say, financial, some financial, if you are trying to get responses on some financial variable, and you use a 10-point scale, and if you apply it on uneducated people, probably it will be inaccurate, right? So, but if you apply it on people who are highly educated in finance, they will easily be able to differentiate between a 9 and a 10. So you need to keep the target respondents in picture while deciding sensitivity of scale. Now, reliability, I told you that it can be, there can be different reliabilities and validities. Now, there are some threats, or reliability can be jeopardized, or it can be lost, not only because of the measure, it can also be lost because of other things in research, like subject variability. Okay, that is when the subject means the respondent variability. When say respondents are in different state, that is either they're tired, fatigued, the mood is good, bad, and at times because of social desirability. Like say if you ask a respondent that do you take drug, no respondent is going to say yes. So at times that variability happens or reliability is lost because the statement that you have used actually touches the social desirability of the respondent. So you need to be very careful while deciding the statements. If any statement is social desirable, it comes into that category, you would find that the respondents may give wrong responses. Observer variability. This observer variability comes into picture when you're using, say, the methods are, or the data is collected through observation. When the data is collected through observation, you find that observer variability will come into picture. Situational variability, conditions under which measurements are made. Like say, in busy day in a shopping complex, or new management has just come in and you're trying to measure, say, satisfaction level of the workers in that organization, you find that there will be difference in the values that you get. So you find that scale would come out to be unreliable when you do that. Instrument variability, you may, the instrument may be understood differently by different people. Now that happens when the wording of the instrument or questionnaire or measure are such that people can't understand them exactly the same way. Every person is not going to understand it exactly the way it is framed. In that case, you find that this can have effect on your reliability. And data processing variability. While using software or when handling data, if there are issues in that, you would find like miscoding, etc., you find data processing also can create that reliability would come out to be lower than what it is. So other than measure, also there are a lot of factors that affect your reliability. And I talked about two types of reliability. One was test-retest reliability, and the other one was internal consistency reliability. But there is one more, which is called inter-rater reliability. And this is generally used while developing your measure, while developing your scale when you are developing, right? Because you will use raters or ones who would rate your instrument. And if there are differences between the raters, then you can evaluate whether the scale is reliable or not. And the characteristic that is used is called kappa. Kappa evaluates the level of reliability in case of inter-rater reliability. Test-retest I talked about. In this case, you collect data using the scale from same group of people once, and after some time again collect data from same group of people using the same scale. And then you try and compute the differences between them. You can compare and you can evaluate whether test retest reliability is, what is the level of test retest reliability. If the responses are same, then and correlation is evaluated between these two. So if the reliability is high, you would find that reliability will go closer to 9 or 9 plus. And in case of reliability being lower, I mean, if the people are not able to understand the statements exactly the way they have been framed, then you find test retest reliability would change from test to test. So it's a test of whether the framing of statements are correct, it has been correctly understood by people. And internal consistency reliability, as I said, is measured using Cronbach's alpha. We will come back to that. Your inter-rater reliability is evaluated using kappa, and kappa is computed using exactly the way that we use for computing your chi-square row values and column values, right? You understand? You remember how do we calculate the estimated values? How do we estimate values for different cells? So exactly the same way is used for computing estimating the values, cell values. And then using this formula, N1 multiplied by N3, this N1 is the total of A and C. N3 is the total of, that means the column and row. A is basically the cell wherein A is marked. The value for that can be computed using N1 multiplied by N3 divided by N. And we know that that is how we compute it in chi-square. And if you manually ever computed, you would know that, right? So you find that you can add this and plus N2 multiplied by N4 divided by N, that is B. A plus B will give you, rounded to nearest whole number, will give you the estimated value. And sum of observed count in A and D. This is how you compute the estimated value. And kappa formula is observed minus estimated divided by N minus estimated. And you will get kappa. And kappa value, high reliability is when the value is almost perfect is 0.8 to 1. Substantially high is 0.6 to 0.8, 0.61 to 0.8. Moderate is 0.41 to 0.6 and so on. So your reliability should be high. That means it should be greater than 0.61. And you can, internal consistency reliability can be computed using a number of methods. Split half is one. Second is Cronbach's alpha. And there are others, Gutman and so on. And the formula used for computing Cronbach's alpha, you will look at that. And similar formula, part of this formula would also be applied in split half. Look at this formula, K divided by K minus 1, where K is the number of items in a scale. Okay, number of items in a scale is the K. K divided by K minus 1. Okay, and multiplied by 1 minus sum of item variances divided by total scale variances. Now this K divided by K minus 1 will also be used in split half. This part multiplied by the correlation between one half and the other half. Now that would be the reliability in case of split half. Whereas in Cronbach's alpha, we don't use the correlation. We use sum of item variances divided by the total scale variance. That means for each item, item means scale item. variances in each item summed together, divided by taking the whole scale, responses on the whole scale together and computing variance there. Now, this is how you compute. And if that means Cronbach's alpha depends on each item, whereas split half depends on sum of half the items one side and sum of half the items the other side. That means a lot of reliability is lost when you compute reliability using split half. That means split half is not a very accurate method. And Cronbach's alpha, because it depends on each item, it is the most accurate method of computing reliability. And reliabilities above 0.7 are considered as adequate, and reliabilities above 0.9 are considered as absolutely good, very good. I'm not going to go into this. Validity we will come to. And since we're talking about measures, and measures should be valid as well, there are four different types of validity: phase validity, content validity, criteria validity, and construct validity. Basically, the first three first two are subjective validities, and the 2, 3, and 4 are the objective validities. Phase validity is reported by the respondent, by the researcher. That means researcher can indicate what is the phase validity of the measure that he has developed, based on and can justify that by quoting the validity of the other scales from where he has taken the items, and can indicate that the phase validity of my measure is high. Content validity is through cross-referencing. That means if each item that you have used in your scale can be cross-referenced, that means can be referenced from the other resources, then that means for each item you can indicate reference. Then you can report that the content validity of my scale is high. And for each of those scales, you can indicate what was the validity for each of those scales. So if none of the scale had lower than 0.7 validity, that means your scale also can be considered as having validity greater than 0.7. So content validity and phase validity, as I had said, are subjective evaluations, because they are not computed based on the responses that you get using that measure. Criteria related validity and construct related validity, these are the two that can be computed based on the responses that you get. In predictive validity, you are using, say you are computing a value today, and you are indicating that based on this scale, there will be a value, you can indicate today, and if that, how much is how closely you are able to predict the value in future. That means if you tell today that this will be if you're using a method of computing that what will be the price of a particular stock after say 5 days, and if that comes out to be true, or how close that comes out to be to that predicted value, would indicate predictive validity. And concurrent validity is when you can check right now that you use a method to compute, say, stock price and compare it with stock price now, that it can compute the stock price of today and you can compare it with today's stock price. And if it comes out to be close, then you can say that the concurrent validity is high. And how close it comes out to be, what level, what is the level, 0.8, 0.9, or 0.95, how close it is. So predictive and concurrent validity are computed like that. Construct validity is the one that is computed based on the data that you collect and it can be computed using exploratory factor analysis, or it can be computed using structural equation modeling. Some of the methods or some of the software that we use for structural equation modeling will automatically compute construct validity for us, like Smart PLS. Smart PLS computes the construct validity and gives reports. Whereas there are others like Amos, etc. If you use Smart PLS, so the structural equation modeling using Amos, it will not give the construct validity. You need to compute using the either Excel, or there are metrics that are associated with it. You can use those metrics and compute, but then it directly does not report. But you can also use the exploratory factor analysis, because what you need for computing construct validity is the factor loads. You based on the factor loads, you can compute the convergent validity. You can compute discriminant validity based on that. These two can be computed based on the data that you get. How can you do that? Convergent validity is reflected by using three items or three reports. That is factor loads, which we get from exploratory factor analysis. The second is average variance explained, that is computed based on factor loads, and construct reliability, that is again computed using factor loads, right? So these three actually reflect convergent or evidence of validity. So if factor loads are greater than 0.7, if average variance explained is greater than 0.5, and construct reliability is greater than 0.7, we will say convergent reliability is established. Discriminant validity is computed using average variance explained and interconstruct correlations. So average variance explained is the variance that has been captured by the instrument, and the interconstruct correlation indicates the one that has not been captured. So if we put this, that means when you compare average variance explained with the interconstruct correlations, and if all interconstruct correlations are smaller than the average variance explained, we can indicate that the extracted variance or variance that has been extracted by the measure is greater than the variance that has not been extracted. That means it has discriminant. It has it is able to discriminate between the statements, or there is a discriminant validity, or it can discriminate between factors. That means there is a discriminant validity. Discriminant validity means within factor, each factor, if it has number of statements, they should measure similar traits. They should be closer to each other. And between factors or between variables, the different variables should measure different aspects of the product, so they should be different. So discriminant validity is when we indicate that the two variables are different, right? And last one is factorial or nomological evidence of validity. Now, this is based on the established theory. That means based on factually, whether if we are trying to show relationship between two variables, whether conceptually those two variables are supposed to be related or not. So if you are able to establish that would come from the research that has already been carried out. So nomological evidence of validity would come from your review of literature. Now that would indicate, based on review of literature, you can indicate that nomological evidence of validity exists. right? So that would be based on your existing evidence that relationship between whatever relationships have been indicated in the model that you're testing through your research have already been indicated that the relationship exists, or conceptually it is supposed to exist. All right, so you can compute validity like that. I have indicated here. So we've looked at measures, basic measures of evaluating different subjective characteristics that cannot be measured objectively. And how can we ensure that these measures that we prepare would be reliable and would be valid? And how can you compute that? So we've looked at that. I think it's 6:36 right now, and we've done first part. The second part we'll be looking at after about, can we take a break of 10 minutes?
Sure, sir.
I think you should take a break of 10 minutes. You are at your places, so have tea and come back in next 10 minutes. So we'll start the other part of our presentation today, and that is based on assumptions. So I will be looking at assumptions in the next session. Okay.
Thank you so much, sir. Everybody will stay logged in. We will just resume in 10 minutes. Please do not leave the meeting.
All right, so I'm also not going to leave. So I'll just have my tea and we'll start.
Okay, okay, sir.
So at 6:45, we'll start. It's about 6:37 now. Right. All right, is everyone back? Can we start?
Yes, sir. Yes, sir.
All right, so we were to evaluate 2-3 assumptions, but I'll be looking at far more than what is indicated, because the maximum number of assumptions that you need to test are in your linear regression. So I'll be looking at all the assumptions that you need to test in linear regression, and that includes majority of the assumptions that you need to test. Now, what are these assumptions, or what is assumption? And why do you need to test your data before you apply any statistical test? Actually, whenever you apply any statistical test, every statistical test requires a type of data. And therefore, whenever you apply data, or whenever you use data for applying a statistical test, it assumes that the data is as per the requirements of the test. That means it is the person who's carrying out research who actually decides the quality of results that you would get using software. Software automatically cannot give you correct results unless you take correct decisions based on the assumptions that are supposed to be there for any test. So you take any statistical test, specifically the parametric tests, and you find every parametric test has its own assumptions. One major assumption for all the parametric tests is that the data is normally distributed. Okay, the data is normally distributed. Now, what does that mean? The data is normally distributed. There is a inverted bowl shape of the probability of the data taking different values. Okay, the probability of data taking different values is represented by inverted bowl. That means it starts from say -infinity, goes up at the mean value. If you look at it, the shape will be, if you track my finger, the shape will be like that. Shape of normal distribution is like this, right? So a normal distribution is used because it has a property of having equal area both sides and so on. So a majority of tests or probability of values using normal distribution is easy to compute. And that is the reason why a base has been used. I mean, for any hypothesis testing, because we are using samples. And let me slightly elaborate on this so that it makes things become clear. Say, if you are taking a population size of, say, 50, let us talk about normality, why it becomes, why it is possible to assume that the data will be normal, and why it is needed, right? So let's look at, if you look at probability distributions, you would come across 3 probability distributions. The probability distribution of the population, or we call it population probability distribution. That means if you are measuring any characteristics of the population, say we measure motivation level of a particular population, right? So you will find that it will vary from a very low value, and then it will rise, and then it will come down, and so that means majority of people would fall in average motivation level. Okay, majority of people would have average motivation level. Very few people will have very low motivation level, and very few people will have very high motivation. Okay, so probability of motivation will be very low, or number of people having low motivation would be very low. Number of people having average motivation will be very high, and number of people having high motivation will be very low again. Right? Similar would be the shape of sample distribution, because sample is supposed to be representing the population. So distribution, probability distribution of a sample will resemble the probability distribution of a population. Now, for computing or for applying any statistical test, we use sampling distribution and not sample distribution and probability and population distribution. We use sampling distribution. Now, what is this sampling distribution? If we take samples from the population and compute the statistic that we want to compute, like say motivation, and we plot the average motivation, probability of the average motivation. Again, the probability of average motivation of all the samples that can be drawn from a population will also resemble normal distribution. Okay, will also resemble normal distribution. Now, a sample may or may not be normally distributed. Population also may or may not be normally distributed. But that means a population distribution may not be normal. The sample distribution also may not be normal. But in all probability, the sampling distribution comes out to be normal. How? It is because of the central limit theorem that applies to it. And why central limit theorem applies to it? Because if you look at, say, population size of 50, and we want to draw a sample of 40 from a sample size of 50, how many samples can we draw? Can anyone tell me? You can you can switch on your mic and tell me. How many samples can you draw of size 40 from a population of 50? Nobody wants to attempt? Guess? 1. Somebody has said 1. So let's see. If you change one respondent out of the sample, replace it with another, it will become another sample. Now, can you tell me how many samples will be there? Not 10. So, somebody has said 10. Combination formula you've read? What is combination formula? Yes, NCR, isn't it? So it will be NCR. N is 50 and C will be 40. You can apply that formula and it will be how much? N factorial divided by R factorial multiplied by N minus R factorial. Correct? N factorial divided by R factorial multiplied by N minus R factorial. So N is 50, R is 40. So 50 factorial divided by 40 factorial multiplied by 50 minus 40, that is 10 factorial. So if you take 40 factorial and 50 factorial can be divided into 50 multiplied by 49 multiplied by 48 up to 41 multiplied by 40 factorial and divide by 40 factorial multiplied by 10 factorial. So 40 factorial will go. And now you will have 10 values numerator, 10 denominator. 10 values numerator will be 50, 49, 48 till 41. And denominator will be 10, 9, 8, 2 till 1. Now, you multiply this and the values will be in billions, at least millions. Now, that means from a small population of 50, if you draw a large sample like 40, still you will get very large number of samples. And central limit theorem states that if there are very large number of samples drawn from the same population, the distribution of those samples would be normal, right? So whether the sample distribution is normal or not, whether the population distribution is normal or not, individual sample distribution I'm talking about, the sampling distribution would always be normal. And that is taken as the basis for testing hypothesis. That means all statistical tests will use normal distribution as a base, that the distribution is normal. Okay. Now, how can you test this? There are two tests that you can apply. One is one sample KS tests. I talked about two sample KS tests while talking about non-parametric tests of differences between two groups. Here, it will be one sample KS test, Kolmogorov-Smirnov test, right? So there are others also, but one sample KS test is a good test to compute the normality. So whatever data that you get from the questionnaire, you can compute whether the data is normally distributed or not. For a summated scale, if you are applying t-test, you need because there are two variables, you would need to apply bivariate normality, and it will not be univariate normality. In case of single variable, you can apply, you can compute using one sample KS test the normality. But when you are using two samples, you need to use but the variable is same, then you can use because since the variable is same, you can apply same one sample KS test. But when you are using correlation, regression, etc., there, because there are multiple variables, at least two, there you will need to use bivariate normality or multivariate normality. So for t-test, etc., since variable is same, you can apply KS test on the variable, and you can compute whether the data is normally distributed. But for regression, etc., you would need to apply multivariate normality, and we'll be looking at how we can do that. So we'll be looking at the presentation now. I will be taking one each assumption, what that assumption means, and how to test. Since there are assumptions that data is this type, unless you test data and report that this is the type of data, till then, your results of the test that you have applied cannot be justified, cannot be accepted on face value, that they are accurate results. But if you look at majority of research papers that have been published across the world, you find very few papers report this assumptions, testing of assumptions. But if you do, publication becomes easier. So I will be talking about each of those assumptions, and I'm sure that once you start reporting the assumptions in your research papers, it will be easier for you to publish. Now, let's see. I'm going to share screen. Are you able to see my presentation? Is it visible? One of you can respond. Okay, that's good. All right. So we're going to look at this assumptions of linear regression. And in that, while covering this, I'll be talking about those 3 assumptions that have been indicated in the for today's coverage, right? Linear functional form is not the assumption that was included, but I will be talking about this because in linear regression, we need to establish that the relationship between the 2 variables is linear. What we do really is, like say, if I want to establish where do we use regression? Regression is used where we want to compute the causal relationship. We want to establish the causal relationship between variables. That means one variable is cause, and its effect is measured on the other variable. That means independent. It will be used where we are classifying variables into independent and dependent variables, right? Like say, if we want to evaluate what is the relationship between customer satisfaction and customer loyalty. That means customer will buy same item, same brand multiple times. What is the probability or what is the relationship between satisfaction and this loyalty? That if the customer is satisfied, will he buy more number of times the same brand? Now, if we want to establish this relationship, customer satisfaction and customer loyalty, we need to apply regression. Now, in normal case, what do? We just use the measure to evaluate the 2 variables. That means we will have a measure to evaluate customer satisfaction, and we will have a measure to evaluate customer loyalty. And then we will compute the totals because it will be summated scales, both of them. And between those 2 columns, we will apply regression. That is linear regression. Without testing whether the relationship between the 2 variables was linear and the other observations, we would report the results. But can we say for sure that these results are accurate? No. So I will be talking about now what are the different tests that you need to carry out to ensure that if we are able to prove all these assumptions, then we can say with surety that the results are accurate. Unless we do that, we can't say for surety that the results are accurate. So I'm going to talk about each one of them. And maximum number of assumptions are in regression. And there are 1 or 2 assumptions that will be in addition to that in AMANOVA and so on. So I'll be talking about them as well. Right, so let's look at linear functional form. That means the 2 variables should be linearly related. The relationship between 2 variables should be linear. Now, it can be checked using, there is a feature called curve fitting. When you go for regression, when you're selecting regression, you can select curve fitting there. And when you select curve fitting, it will give you a number of models that you can select. And if you select all of those models, it will compute the relationship, whether all those, that means, you can measure the multiple relationships. What is the relationship between the 2 variables? And when you look at the results of those, and you see whether it is closer to the linear curve, or it is closer to the relationship, or it is closer to any other curve, is indicated by the 2 values, that is R square, which is a regression coefficient. So when you do the curve fitting, it will report R square and F value for all the curves. And one of those curves would be linear curve. So you prepare a table of R square and F and see which R square and F are highest. Now that is the best, that is the closest fit to the data. So if linear curve has highest value of R square and F, we will say the relationship is linear. And if there are multiple curves which have highest R square and F, and if linear is one of them, again, we can say the relationship is linear. But if linear values are lower than and considerably lower than the other curves, that means the relationship cannot be assumed to be normal, right? So that is one that you need to test whether the relationship is linear. Second is independent observations. Now, independent observations are a part of design, your research design. How do you ensure that the observations are independent? Now, when we independent is, in case of, say, I will first try and indicate using a test of differentiation for indicating independent observations, and then I'll come back to regression. Now, in tests of differentiation, like say t-test, there are, and say if the test we are applying between male and female, and say we are applying between the quality of this presentation evaluated by male participants and female participants, and say we try and differentiate between them. Now, when we collect data from male and female participants, and we divide these into two groups, male and female. Now, we are not including any female in the male group and any male in the female group. So data collected in female group would be from female respondents, and in male group, it will be from male respondents. So that means the samples are independent of each other, or the data observations are independent of each other, right? Now, these are the independent observations. That means the observations are independent. Now, let's look at the other side. If I collected, if we were to collect the knowledge or data on understanding of assumptions before this session and after this session, and all of from all the respondents. Now, this is what is called dependent observation, because the samples are dependent, because same sample is going to be used to collect data twice, right? So independent observations and dependent observations. Now, dependent observations would be when the two groups, when the data is collected from the same group multiple times, right? So this is a normal case. And I have written for that normal case. But in regression case, there is a slight difference. Actually, I changed this just before starting this presentation, basically because I wanted you to understand independent observations in case of the other tests also. Because in other tests, these samples need to be independent. Whereas in case of regression, the sample cannot be independent, because the data has to be collected from on both the variables from same people. Then only you can develop relationship. Okay, you need to use same sample for collecting data on both the variables. Like say, if I said customer satisfaction and customer loyalty, then you need to collect data from same people on customer satisfaction and same people on customer loyalty. That is how one-to-one correspondence would develop. And that is how we will be able to indicate whether there's a relationship, cause and effect relationship between customer satisfaction and the customer loyalty. Now, then what does this independent observations mean in case of regression? Now, it means two things. One is that each item in the scale is independent. That means when we collect data from on one statement or one item, and then we collect data on the another item, the wording of one statement do not affect the observation or the response given on the second statement. Now I'll tell you how can it actually influence, and what care do you need to take in designing your questionnaire so that the observations become independent. Now, one is that there are at times you can actually have statements that are emotionally loaded. Okay, you can have emotionally loaded statements in your questionnaire. Like say, I'm going to use two statements. One is that the quality of mother dairy milk is as good as mother's milk. And the second statement is that quality of mother dairy milk is very high. Now, what I have done, the first statement is emotionally loaded, and that would have effect on the second statement. Every respondent going to tick on the highest value of that the quality of mother dairy milk is very high, because of the first statement that the mother dairy milk is similar to or equivalent to mother's milk. Now, that is what we need to take care, that we shouldn't use emotionally loaded questions in our measure when we develop. The second is that when we develop a sequence of variables in our questionnaire, generally what we do, all the independent variables would be listed first, and the dependent variable will be listed last. And that creates problems, because when the respondent gives responses to independent variables, like say, if a respondent is giving high value on customer satisfaction, and your evaluate second variable is repurchase intention, that are you going to purchase again the same product. If he has given high, and after that you are collecting data on repurchase, the customer is going to say, yes, I'm going to buy, because he is not going to independently evaluate his repurchase intention. He is going to evaluate based on what values, what response he has given to his satisfaction level. Now reverse it, that repurchase intention data you've already evaluated. First variable in the sequence of the questionnaire is repurchase intention. Now, when he goes for satisfaction, now can he change this response independent repurchase intention? No. And is he going to do that? No. And his satisfaction level is going to independently talk about now, because satisfaction is not dependent on repurchase. So whenever you develop a questionnaire of multiple variables, your dependent variables should appear first in the sequence, and all your independent variables should come later, so that the observations are independent of on each variable are independent of the other variables, right? So this is a method. This can be embedded in your design, research design and questionnaire design. These are the two things that you can do. Next is normality of the residuals or errors. We talked about normality of a variable. Okay, that we can normality is nothing but probability of different values. Okay, probability of different responses would be normally distributed. That was normality of a variable. But here we are not talking about normality of the variable, because there are two variables now. So we need to establish bivariate normality and not univariate normality. We are not measuring normality of a single variable. We are measuring the normality of two variables combined together, because they are into relationship. Now that can be done by evaluating whether the residuals are normally distributed. And residuals are errors. Now, in case of regression, the estimation line and the actual values, the gap between estimation line and the actual values is called errors or residuals. Now, when you plot these residuals and errors and test their normality, if they are normally distributed, then we can say that there is a bivariate normality. And for testing normality, I said KS test can be applied. You can also use Shapiro-Wilks test for doing the same. Now, Shapiro-Wilks test is considered as a small sample test, and KS test is considered as a large sample test. But what do we mean by small sample test? Is it good enough only for a very small sample? No. Actually, up to the sample size of 500, Shapiro-Wilks generally gives you correct, accurate results. Up to 500, up to 2000 also in some cases, Shapiro-Wilks has been found to be giving correct results, but not in all. So therefore, above 500 sample size, we should not use Shapiro-Wilks, and we should use Kolmogorov-Smirnov single sample test called KS test. Right? Kolmogorov-Smirnov test actually gives accurate results for large samples, and it is slightly inaccurate in case of smaller samples below 200. So for below 200 sample size, we should use Shapiro-Wilks only and shouldn't use KS. And for above 200, we can use KS. Right? So you can compute the normality, and whether the sample is normally distributed or not, Shapiro-Wilks and KS test actually test a hypothesis that this sample is normally distributed, and it should not get rejected. Right? So the sample, the level of significance should come out to be greater than 0.05. If it is greater than 0.05, then this hypothesis that the sample is normally distributed is not rejected, and therefore the sample remains normally distributed. So this is how you test normality of residuals or errors. Okay. All right. So we've looked at normality. Equality of variance of errors, homogeneity of residual. Now, homogeneity can be considered, homogeneity of variance can be considered when you are looking at two groups also. Homogeneity of variance, like in case of say t-test, and homogeneity of variance in case of ANOVA. In case of ANOVA, it is important, very, very important, homogeneity of variance. Homogeneity of variance indicates that whenever you're using multiple groups, then the variance of one group, okay, should be equal to the variance in the other group. That means whenever you are computing T, or whenever you are computing ANOVA F, now that should not be inflated because of the variance in the differences in variance, right? And therefore, this homogeneity is tested, and it is tested using Lewin's test. Okay, homogeneity is tested using Lewin's test of homogeneity. So that means you can apply Lewin's test of homogeneity, and it equality of variance, we call it Lewin's test of equality of variance, and it will evaluate whether the variances are equal or whether there is a homogeneity that exists. Now that is for Lewin's test is for in case of ANOVA, and in case of regression, we apply scatter plot. And in scatter plot, we see the deviation of actual values from the predicted line. If the deviations are small, deviations of actual plot are small with the predicted line, that would indicate that variances are equal. The homogeneity of residual variances is established. Okay, so it is done through graphical test. Next is no autocorrelation of errors. Now, what is an autocorrelation? And if some of you have finance background, you would know what autocorrelation is. Autocorrelation is more important, or it becomes serious in case of time series data. But in case of regression also, it inflates your R square, that means regression coefficient, if there is autocorrelation that exists between within the variables. Now, autocorrelation is when within the variation, there is a relationship between the observations within the same sample, within the same variable, right? So if there are, say, there's a sample of 200 people, responses given by different people, if there is a correlation between them, high correlation between them, then we will say there is a autocorrelation between the values. And how do we test it? If there are 200 respondents, now in one series we will have 1 to 200, 1 to 200. In the second series we will have 2 to 200. So in one 1 to 199, and second 1 to 2 to 200, and these will compute the correlation. Now that would indicate autocorrelation because it is going to measure relationship between 1 to 2, 2 to 3, 3 to 4, 4 to 5, and so on, right? So if autocorrelation is high, it inflates a regression coefficient, and in number of other tests also, in correlation also, it affects. So we must measure autocorrelation. Even in case of number of other tests, autocorrelation is a problem. So we must ensure that autocorrelation is within limits. And it can be tested using Durbin-Watson test. And the values of Durbin-Watson between 1 and 3 are in 3 indicate that it is within limits. If it is below 1 or above 3, it is beyond limits. And therefore, then the data needs to be corrected before it can be used for regression. In eViews software, there are methods of correcting. In regression, in SPSS, there are no method. There is no method for correcting the autocorrelation. If it is there, it is there. But in eViews, you can apply the if there is high autocorrelation, it is better to use eViews for regression, and you have methods of ensuring that it can be cured. The data can be corrected for autocorrelation. So if your autocorrelation comes out to be lower than 1 and greater than 3, then you must use eViews and not SPSS. Now, next is outlier distortion. Now, outliers we must be conversant with, all of us. When we have a sample, and within the sample, if there are respondents who have given entirely different response on the variables of study, then we will consider them as outliers. That means, and for considering a person or a response as outlier, we use limits. And those limits are drawn at either plus and minus 2 standard deviations or plus and minus 3 standard deviations. Plus and minus 3 standard deviations means 99% line, and plus and minus 2 means 95% lines. So that means plus and minus 2 standard deviations indicate that 95% of people would fall within that. And plus and minus 3 standard deviation means 99.67% of the respondents would fall between that. So we can draw these two lines, and respondents who have values beyond these lines, the 2 lines, they will be called outliers. And these outliers can be checked using explore under descriptive analysis in SPSS. And these outliers can be deleted. That means respondents who have given entirely different response than the others can safely be deleted. There may be people who have given responses without reading, or they have given responses that are one-sided, either too high or too low. And therefore, they will distort your relationships, and therefore they can be deleted. And we must apply regression only after deleting them. So they can be, and this outlier distortion can be checked on the report that is generated after regression. Okay, the report on regression also has a report on outliers. It reflects a number of outliers, the respondents who are outliers, and can easily be deleted, and regression can be reapplied. And in fact, when I talked about normality of residuals, if in the initial time, if your normality of residuals is not established, you can delete all the outliers, and you find that normality it is more likely to be normal than otherwise. So if there are outliers, they also affect your normality. So you can delete outliers so that your relationship, the residuals become normally distributed. And also, because you have deleted outliers, the relationship becomes better between the independent and dependent variables. Zero sum of errors is established by sum of squares. The regression, it depends on regression method, and the method generally used is the one that automatically ensures sum of squares are 0. So we don't need to actually test this. Next is representative sample and proper specifications of the model. Now, representative sample can be computed using statistical formula, and we can compute what is the minimum sample size that is needed for regression. And but then there are issues with the statistical formula, because it uses z squared divided by standard deviation squared multiplied by error squared is the formula. That means z values can be taken from the table, but standard deviation, how do you compute without selecting a sample? And sample size is generally required when you submit your synopsis if you are doing your PhD. And since you don't have the standard deviation, you can get this standard deviation values if similar studies have been done on similar variables or same variables elsewhere. But generally and specifically, it should also be that the respondents should be similar. Then you can take that as the standard deviation, but you can get closer. Standard deviation or closer values, you can go closer to standard deviation by using the standard deviation that has been obtained by the other researchers using same variables. That can be done, but still you would not be very accurate. It will still be rough. And the second part is more important, and that is error term. Error accepted. Now, error accepted, if you say that your error accepted is equivalent to the, say, type 1 error, and that is equal to level of significance. Type 1 error is level of significance. So if you consider error accepted. The error accepted is type 2 error, actually. So generally, we try to bring these two errors equivalent to each other, so that and that is the time when these two errors are minimum, type 1 and type 2 errors, right? So you can indicate equivalent to that. However, number of times there will be questions that how can you say this is a safe error of the assumed error? You could have considered, you could have gone in for even better results by having this error as smaller. So there is no value that would that you would be able to justify 100%. So this creates a bit of problem. Now there is a acceptance that okay, error can be taken equivalent to level of significance, but standard deviation has to be computed. And that means when you carry out a research, you can do progressive computation of sample. That means you collect data from a smaller sample, compute standard deviation, compute the sample size required. It will indicate a larger sample. Again, you go closer to that, and then again compute standard size, the sample size, and you'll find that a time will come when you get exact sample size. So you can, but not in the beginning of research. Progressively, you can come by using the statistical formula. You can come, right? So sample size should be representative, that you can do by that. And the second is that your model should be properly specified. That means the relationship between independent variables, mediating variables, moderating variables should be conceptually correct. Okay, I talked about, while talking about validity, nomological validity, I talked about it. So you can, based on your review of literature, you can properly define your model. And unless it is properly defined, the regression would give you wrong results. So your model has to be correctly defined to get correct results. And the last one is multicollinearity. Now, what is multicollinearity? This comes in when we have multiple regressions. That means independent variables are more than one. If independent variables are correlated, if there is a high correlation between independent variables, that creates a condition of multicollinearity. And multicollinearity inflates your regression coefficient. That means your regression coefficient will no longer be accurate. It will indicate higher relationship than normal. Now, it is tested using a test called variance inflation factor, VIF. That is reported in your regression results. And if you select, then only. So, and it is computed using 1 divided by 1 minus R square. R square is your regression coefficient. Now, the values between 1 and 10 are acceptable. And beyond 10, if there are any values beyond 10, it does not go below 1. VIF values never go below 1. They can only go beyond 10. So if they go beyond 10, then regression coefficient becomes unsatisfactory. You can't use that. So we must test the data for multicollinearity as well. So what I have talked about right now, this is the last one. What I have talked right now is that your data must meet the assumptions requirement of the test. You will find that every test has assumptions, and majority of those assumptions I have talked about with regression. So you'll find majority of are common, but one or two assumptions may be different. In case of, as I had said, in case of ANOVA, the sphericity would be a different, or repeated ANOVA. In case of repeated ANOVA, sphericity is a different assumption, that it should be within limits, sphericity. The sphericity is actually when you have the groups, group 1, group 2, group 3, because in ANOVA you will have groups, or we will have samples, and differences between sample 1 and sample 2, sample 2 and sample 3, and sample 1 and sample 3. Now, they should be equal. Okay, that is what is sphericity assumption in case of repeated ANOVA, which is different from regression. So we've looked at majority of these assumptions, and I'm open to questions if there are any.
So there's one question which says, which VIF should we consider, centered or uncentered, as eView gives both?
eViews gives both. If you look at SPSS, it gives you only one, and in case of eViews, you must use a centered one, centered VIF, and not uncentered VIF.
Okay.
I'll stop sharing so that we can see each other.
Yes, sir.
And this two values are reported only in eViews. If you look at SPSS, it will give you only centered.
So there's a question from Ms. Madhu. She's asking, what does the uncentered VIF convey?
See, this when you look at variance inflation factor, we look at, if you look at the computation, it is 1 divided by 1 minus r square. Okay, 1 divided by 1 minus r square. Now that is the centered VIF or variance inflation factor. I haven't used the uncentered VIF because I haven't used, normally I don't use eViews. Generally, I'm using SPSS because I use panel data, and I haven't worked on the time series much. So therefore, I won't be able to tell what is uncentered VIF. But centered VIF, I can tell you that it is computed using this formula. All right, you can ask any other questions, because there are too many assumptions, and you need to satisfy all of them if you are using a regression. If you are using any other test, for t-test, there are only two, three assumptions. For ANOVA, there are slightly more. For multiple ANOVA, there are more ANOVA. So you find that for each of those tests, there are different number of assumptions. We must know all of them. And if you search on Google, you would find that all these assumptions are listed, and how to test each one of them. You can go deeper, and you can also check how each one of them can be tested. Can we use SPSS for penal data? Yes, we can use SPSS for penal data. Time series data cannot be tested using SPSS. Yeah, you're right. That Stata gives you, everyone doesn't have option of going to Stata, but SPSS also gives you correct results if you use penal data on SPSS.
Sir, I have given the participants the right to unmute themselves. So if anyone has
a doubt, they can ask me questions. Yes, no issues.
Yeah. Good evening, sir.
Good evening.
Madhu this side. Sir, the problem I'm facing is that even after the transformation, even after log transformation and taking an inverse of the variable, the homoscedasticity cannot be achieved. The data is still heteroscedastic. So what is the last resort, sir?
Actually, before you take this data to your reviews, you could have checked for your outliers. There must be outliers.
Sir, I have removed the outliers.
So you removed outliers.
Yes,
outliers in reviews you can remove outliers. So you have removed outliers and you've gone in for log.
Yes, sir.
You've computed logs.
Yes, sir. I have computed logs.
Okay. And still the data is heteroscedastic.
Yes, it's still heteroscedasticity is showing.
It generally heteroscedastic generally it doesn't, and if it is still heteroscedastic, you are using stock data.
Yes, prices? Sir, I'm using stock data.
That is a possibility, because in stock prices only heteroscedasticity is possible in even after you've computed your logs. There are methods in EViews that you can use stationarity, etc. You've used stationarity?
Yes, sir.
And you are not able to get stationary data?
Sir, actually, this is, even though this is a stock data, this is actually, I'm working on IPOs, that at what price do the IPOs get listed. So it's not a time series data. So stationarity is not causing any.
It's not required. It is not required.
Yeah, stationarity is not required for this data.
If it is now, okay. All right. I mean, you can go for, but if you go for if you go for log, relog, or log of log, you can get, but then the variability of the data would be removed. And the relationship that you are going to get is going to be affected by. In fact, even in when you compute log, you find that the relationship gets reduced because you computed log. And if you go for the relog or second log, then that variability would reduce further, and the relationship will come out to be smaller. So this data, I personally feel it will be difficult. But how much is this heteroscedasticity? What is the value?
I do not exactly remember. I'll have to check.
If it is minor variation, it is acceptable. Even if it goes slightly beyond the level, but if it is very close to the limits, you can still use.
Okay, I use actually Brush-Pagan test for checking heteroscedasticity, and it was coming to be heteroscedastic.
I understand. But then you look at the values. What are the values? If they are very close to the limit, they're very close to the acceptable values, you can still use. And if there is a variation, wide variation, then probably you can't use the regression. And what you can do is you can use it on. You try it on SPSS if it doesn't have autocorrelation, because you are not using time series. So try if there are normally distributed samples. The problem with the stock prices are that they are generally not normally distributed. And that is the reason why you can't use SPSS. But see if they are normally distributed, you can try it on SPSS.
Okay, sir. Thank you. And sir, one more issue I'm facing was that in my regression equation, when I'm taking log of the other variable, the second independent variable comes out to be significant. If I'm taking the normal of the first variable, independent variable, the second variable is not coming out to be significant. So the log transformation is impacting the other independent variable as well.
It does. It does, because if you are having, it is, log is not affecting the other variable, it is affecting the relationship.
Yeah, it is affecting the relationship. It's coming out to be significant.
It does. That's what I said. Log affects your relationship.
So
It does.
relationship of the other independent variable is also being affected by taking log of the other variable, right?
See, if one of the variable is log and the other variable is you not taking log of, the relationship would naturally change considerably. Either you take log of both, or you don't take log.
Okay. Sir, we can't take like log of one variable and the one is the normal variable.
No, then the results will not be accurate.
Okay.
It is.
So if I'm
Yes.
having two independent variable, both should either be raw or should be log transform.
Yes. Then only you will get correct relationship.
Okay, sir.
Ji.
Thank you, sir.
Welcome. Okay, if there are no questions, can we wind up this session?
So, yes, sir. Thank you so much, sir, for the session. We know how busy your schedule is, but in spite of that, you agreed to share your knowledge with us. So we are really thankful to you. And I would like to thank you on behalf of the entire team of Indian Accounting Association and the TLC Ramanujan College. Thank you very much, sir.
Welcome.